let's look at another tool for determining whether series with mixed signs converge. This is the alternating series test, and the idea is we'll look at series where they alternate between positive terms and negative terms. And this is going to look a little weird at first, but what we're going to do is assume that we have a sequence that's always positive, that's decreasing, and that eventually goes to 0. Then we can make this alternating series by attaching a minus 1 to the n plus 1 to it. And so the minus 1 to the n plus 1 just makes sure that now the series is alternating between positive and negative terms as n increases. It turns out that any series of this form automatically converges. And so we could look at a picture of what this looks like. And so first of all, I'm going to graph the sequence minus 1 to the n plus 1 times b sub n. And so that's not the sum here. Instead, it's just the terms in the sequence. And so what we've said is that the sequence is positive, the b's, but now we're attaching it to a minus 1 to the n plus 1, which is going to make it switch back and forth. And then the sequence is also trending towards 0. And so if I plug in a 1, the minus 1 to the n plus 1 is going to be a positive 1. And so I'm going to have some value b sub 1 here. And then if I plug in a 2, now I'm going to have b sub 2 times negative 1. And so that'll give me a minus b sub 2. And then I'll get a b sub 3, and then a minus b sub 4, and then a b sub 5, and then a minus b sub 6. And the fact that the b sequence is decreasing just means that each one of these terms has to get closer and closer to the x-axis here as n increases. And so now we can look at the partial sums of the series. And so in other words, what happens if we add these b's together each time? And so I actually could write the x's down here, and we'll see why in a second. Now I'm going to let, again, s sub n be the sum of the first n terms in this series. And so if I do that, first of all, s sub 1 is just the sum of the first term, which we already know is b sub 1. And now if I want to get to s sub 2, then I just have to subtract b sub 2 from this. And then the next thing I'll do to get to s sub 3 is add back on b sub 3. And then I could subtract b sub 4 to get s4, and then I can add b sub 5 to get s5. And then I could keep on going like that. And so you could see that every time I'm going to alternate between going up and down over and over again. But the point is that the distance between these dots has to decrease every time because my sequence b sub n is decreasing. And also the distance between the dots needs to tend to 0 because b sub n tends to 0. And so overall that means that these dots have to collide to some limit right here, which is the same as saying that my series converges. The alternating series test is typically very easy to apply, and we'll look at a couple examples here. And so the first one is minus 1 to the n over n. And so here, all we need to check is that the sequence 1 over n is decreasing down to 0. And that means that minus 1 to the n over n, this is an alternating series. And it converges by the alternating series test. It's also good for us to keep track of whether or not series converge absolutely or conditionally. And in this case, since the sum with the absolute value, or in other words, if I just drop that minus 1 to the n, diverges because it's the harmonic series, or in other words, by the p-test, now we know that the sum that I cared about in this problem, minus 1 to the n over n, converges conditionally. And so again, that converging conditionally corresponds to the case where the absolute value diverges, but the original series converges. If the absolute value of the series had also converged, then we would have said that the series converges absolutely instead. All right, one other example for the alternating series test is that we have to be careful about when things are alternating because that's not the only condition for the alternating series test. And so for this example where we have the sum from n equals 1 to infinity of n times cosine n pi, first of all, cosine of pi is minus 1, cosine of 2 pi is 1, cosine of 3 pi is minus 1, and so on. And so this is just notation for minus 1 to the n. And so it is the case that this sequence is alternating. However, the n out front is making the sequence explode. It's not tending to 0. And so the fact that the limit as n goes to infinity of n times minus 1 to the n does not exist because it alternates, that means that even though this is an alternating series, it still diverges. And this diverges by the nth term test. As a reminder, that nth term test is what tells you to look at the limit of your sequence, and if the limit is not 0, then you know that the series must diverge. If the limit is 0, you have to try something else. But fortunately, in this case, the limit was not 0, and so we're done.